Chapter 2, Chemistry of Life. So, this was one of the first periodic tables that we came up with, that scientists came up with, I should say. And it always just really amazes me how they knew that they had missing areas, right? They were like, man, we haven't discovered them yet, but we know. To have that ability to know. And then now today, if you really look at a periodic table carefully, this is actually the best cheat sheet ever made. You just have to know how to use it, okay? So, sorry, I jumped in the periodic table. I love the periodic table. It's, once I learned how to use it, best thing ever. Anyways, matter. Anything that takes up space and has mass is matter, right? Cells are the smallest unit of life, right? We remember that from chapter 1. But matter is not limited to all living things. You can have matter and not be considered alive. A rock, for example, has matter, it takes up space, it has mass, but it does not abide by the A characteristic of living things. So, an element is a substance that cannot be broken down to other substances by chemical reactions. So, what are elements? Well, you've got plenty of examples right here. You've got your hydrogen, your carbon, your oxygen, your nitrogen. These four, your CHON, C-H-O-N, CHON, make up 96% of all living matter. Now, right there, we have 92 naturally occurring elements in this periodic table. 25 of them are essential to life. These four make up 96% of every living thing. Let's talk about that again. These four make up 96% of every living thing. So the remaining 4% is what the other 21 are made up of. A compound is a substance that consists of two or more elements that are combined in a very specific ratio. Your salt, your NaCl, sodium and chlorine, bonding together to form salt. Gas on its own, when it comes together and bonds, it's an actual solid. Right here, anybody know what that one might be? I'll give you a hint. Well, it's not cooperating with me right now. But this right here is a hydrogen. This is a hydrogen, and that's an oxygen. So H2O, that's your water molecule. And this one right here is actually has 6 carbons, 4, 5, 6. It has 6 oxygens, 4, 5, 6, and it has 12 hydrogens. This is your C6H12O6. This is your glucose. So, those remaining 21 elements we need in very small amounts, minute quantities. These are our trace elements, right? Because we've got the CHON making up 96% of living matter. Of the 25 remaining ones, which is 21, 25 minus 4, 21, we need in very small amounts. These are your iron. This is your iodine. This right here, these are goiters. Goiters develop from lack of iodine. Okay, when you buy salt at the grocery store, it actually says iodinized salt because it has iodine in it. So most developed countries do not have an iodine deficiency, so goiters are not very common. However, in developing countries, that access to the iodinized salt is not always there, so oftentimes goiters become a problem. Iron deficiency, some of the signs and symptoms of these include having your fatigue, that shortness of breath, depression, hair loss, brittle nails, increased sensitivity to cold, frequent headaches, restless leg syndrome. This is all from a lack of iron. Now, your iron is going to be found in your red meats. A lot of times people can actually cook their food in a cast iron skillet to go ahead and get iron into their body that way. But the problem with having a lack of iron, this leads to anemia. And anemia is basically where your oxygen levels are lower than normal. You can breathe in all the oxygen you want, but if you don't have that iron, which has iron right here, a +2 charge, and your oxygen has a -2 charge, our red blood cells need that iron on there to go ahead and grab that -2 to the +2 and then carry it around, right? Opposites attract. How in the world did I get the +2 and -2? I'm going to explain that in just a little bit. Atoms. So cells are the smallest unit of life. Atoms are the smallest unit of matter, and they still retain the property of that element. Your subatomic particles, these are the units that actually make up your atom, therefore they're smaller than them, include your protons, which have a positive charge, neutrons that have no charge, and your electrons, which are on the outside of the atom, outside the nucleus, have a negative charge. So your nucleus is made up of protons and neutrons. And these guys have most of the mass of your actual atom. So if we ask about the atomic mass, we're actually asking about the number of protons and neutrons. Your atomic number is simply your number of protons. Now, we're not saying electrons don't have mass. It's just that their mass is so small compared to the protons and neutrons, we don't take it into account. For example, if you have an elephant getting on a scale and a leaf falls down on that scale, are you going to stop everything and take the leaf off the scale? Or are you just going to leave the leaf right there and go ahead and take the mass? You're going to take the mass because compared to the actual elephant, that leaf has very little significant mass. Now, we've got our atomic number of protons, our atomic mass, protons plus neutrons. So what's an isotope? Okay, you cannot change your number of protons, you cannot change your atomic number and remain the same element. Let's go back to the periodic table again. Hydrogen has 1 proton, helium has 2 protons, that's their atomic number. So if helium loses a proton, he becomes hydrogen. He's no longer helium. He can have a different number of electrons, and he can have a different number of neutrons. He cannot have a different number of protons and remain the same element. So, an isotope is where you have a different number of a different number of neutrons than you had. If you change the number of neutrons, you are an isotope. If you change the number of electrons, you're an ion. That's not on there, I'm just throwing it out there. But you cannot change the number of protons and remain the same element. So, let's talk about the periodic table's patterns. There's something called the octet rule. All right? Right here, the octet rule. Think of octopus, octagon, octet rule. They all have the same thing in common, the number 8. And what's very interesting in a lot of different cultures, the number 8 is actually a lucky number. So I always think that's interesting. The octet rule states that you have to have 8 electrons in your outermost shell to be considered full. So, if you're in group 1, this first column, you only have 1 electron in your outermost shell, or 1 valence electron. In this one, you in group 2, you have 2 valence electrons. These guys in the middle, we're going to skip them. They're more complicated than we need to go. So we're going to jump to technically group 13. So you would think it'd be 13, right? Because group 1 was 1, group 2 was 2. This guy's got to be 13. No. Because remember, the magic number is 8. So group 13 has 3 valence electrons. Group 14 has 4 valence electrons. Group 15, 5 valence electrons. Group 16 has 6 valence electrons. Group 17 has 7 valence electrons. Group 18 has 8 valence electrons. Oh, that's the magic number. So anybody that's in group 18, they are the noble gases. They are not going to bond with anybody because their outer shell is full of electrons. So they don't need anybody. But chlorine here, he's in group 17. So he's got 7 valence electrons, right? Remember sodium? Whoop! He's right here in group 1. He's only got 1 valence electron. But 1 plus 7 gets you to 8. And that's why sodium and chlorine bond together to make salt. So let's do these real quick. How many valence electrons does sulfur have? Sulfur is right here. He's in group 16. This particular periodic table doesn't show you the group numbers. I apologize for that, but it's group 16, I promise you. Okay? So he has how many valence electrons? 1, 2, 3, 4, 5, 6. So sulfur has 6. Helium. Helium's in group 18. Now, I did fib to you just a little bit. There are 2 exceptions to the octet rule, and they happen to be the 2 at the very top, hydrogen and helium. These 2 do not need 8 electrons in their outermost shell. They just need 2. It's still the same concept though. They still have to have a full outer shell. That's why helium's all the way over here, because he's part of the noble gases. Because if he has 2 electrons in the outermost shell, he's happy. He's not going to bond with anybody. Hydrogen, on the other hand, he's like, whoa, whoa, I still need 1 more. So these 2 only need 2. So helium has how many valence electrons? He's got 2, but he's full. Chlorine, we talked about that one. He's in group 17. He's right there. He has 7. Xenon, xenon's in group 18, right? He's right here. He's one of the noble gases, so he has 8 valence electrons. So who would they bond with, right? If we're talking about magnesium, Mg has got a +2. So Mg's got a 2 electrons. We need 6 more to get to 8. So magnesium oxide. Ooh, look at that. Mg can go with O. Hydrogen. Who can he bond with if he's got 1? He can bond with fluorine, hydrofluoric acid, or HCl, hydrochloric acid, right? Now there's something else hydrogen can do. Hydrogen can bond with oxygen. But wait a second, oxygen only has 6. 6 plus 1, that's not going to work. That only gives me 7. I need 8. Okay, well how about if I have an extra hydrogen? So now I have 2 hydrogens, so 1 plus 1 plus 6, that gets me to 8. And that's why H2O has that particular formula. Okay? So in trying to reach the octet rule, certain bonds are made, right? That's just your lambda, and that's just saying it is a partially positive, and that's a partially positive. So the hydrogens are partially positive, and the oxygens are partially negative. Why? Well, here's our water molecule. We've got the 2 hydrogens, right? Each hydrogen has 1 electron. Our oxygen has 6 electrons in the outermost shell. He needs 1 more, so they're all sharing. But that electron is going to go all the way around the oxygen and then do a quick loop around the hydrogen, and then quick loop around this hydrogen, and then a long loop around the oxygen. So if you are an electron, where are you spending most of your time? In the hydrogens or in the oxygens? You're going to spend in the oxygen, right? Because it's so much bigger. Well, that gives a oxygen a slightly negative charge, because remember, it's an electron, and electrons have what kind of charge? That's right, they have a negative charge. Covalent bonds, this is where the electrons that are shared between elements in order to make molecules, because there's not enough of a pull between the 2 elements. Your oxygen is not going to pull the electron completely away from the hydrogen. You can't do that, okay? It's going to share them. It's not shared equally, but it's shared. So covalent, think of couples, they share. Ionic bonds, this is where the electrons are stolen or they're given away and they make compounds. Like right here. Sodium, if you're sodium, you're in group 1, you have 1 valence electron, right? So you need 7 more to reach that 8. Or you could just get rid of 1 and drop down to the previous level. Chlorine, he's got 7 valence electrons. He just needs 1 more. So what's easier for him to do? Get rid of 7 or find 1? He finds 1. He found it from sodium. And that's why they formed that bond. You see right here? That 1 electron that was on the outermost shell of sodium, it jumped ship and it went over here to chlorine and formed those 8. So that's an ionic bond. They're the stealing and giving away of electrons. Covalent, couples share. They share the electrons. Your chemical reactions. This is where we make and break chemical bonds. Your reactants are what react to produce the products. Your reactants are go into the reaction and your products come out of the reaction. It's just that simple. Now, would there be any life without water? Absolutely not. Terrestrial life today still requires water to survive. We can survive weeks without food, but we cannot go longer than 1 week without water. 90 to 95% of our cells are made of water. 3/4 of our Earth's surface is made of water. It is present in all forms, liquid, solid, gas. It is important for life. When they were looking for evidence of life on Mars, the first thing they were looking for is the presence of water. So, properties of water. Remember how we talked about the oxygen slightly negative and the hydrogens are slightly positive? That's what we call polarity. Because we have that uneven sharing of the electrons, there's a positive and negative charge. So when I throw sodium chloride in here, the sodium that has a +1 charge goes to the oxygen, and the chlorine that has a -1 charge goes to the positive, because opposites attract, right? Well, that polarity and cohesion are two of the things that allow water to be the universal solvent. That's a liquid that is completely mixed of two or more substances. Let's talk about pH, right? Our pH scale is from 0 to 14. 7 is neutral, right? That's true pure water. Our blood is actually about 7.5, okay? Anything less than 7 is an acid. Anything greater than 7 is a base. Oh, look at that, right? What comes first in number line, 0 or 14? 0. What comes first in the alphabet, A or B? A. So, less than 7, you're an acid. Greater than 7, you're a base. Apologies. And 7 is just neutral. Notice your cleaning products are very basic. Notice your coffee, your orange juice, our stomach acids. These are all much more acidic. Okay? Cohesion. Again, right? Coworkers. Water bonds to other water molecules. So when you are two alike things bonding together, you are cohesive. You are a cohesive unit, right? Cohesion. Work together, you're the same. Adhesion is where water bonds to something else. So for example, think of the water bonding to, tape. If I take tape, like I'm talking Scotch tape, right? And I take Scotch tape and I put the Scotch tape to a piece of paper and I put it on the wall. Are the paper and the wall made of the same things? Are they the same atoms? No, right? But I have just bonded them together even though they're two different things bonding together. So that's your adhesion. And by the way, the other name for Scotch tape, if you happen to buy tape that's not Scotch tape, is adhesive tape, because it's referring to this particular property of water. Your capillary reaction. Water can be pulled up against gravity in very small, narrow tubes. And that's what you find inside these giant trees, is these really small, skinny tubes. I mean, think about a straw. When you're drinking, if you use the straw like a milkshake straw to drink your soda, you're going to be sucking on that straw really hard and you're not going to get that water going up really high, right? You get a skinnier straw. So based on the thickness of the liquid, you have to get the right width of the tube so that capillary action works properly. Surface tension. All right, how difficult it is to break the surface of a liquid. The basilisk, for any Harry Potter fans right there, that's your basilisk lizard, also known as the Jesus lizard, because he is able to run on water. He has to have a good enough space to take off, and then he will run at the fast enough that he does not break the surface tension of water, so that it actually can run across the water and not fall through the water. Freezing. What happens as water freezes? Well, the molecules expand. The water properties, the bonds between the hydrogen bonds between the water molecules, push the molecules away from each other. And because mass divided by volume gives us density, This allows the ice itself to float. Well, why in the world is that important for living things? Well, if water, when frozen, sunk, if it became denser, then every pond, every lake would freeze from the bottom up every single winter. That means that everything living inside of it would die. By water freezing upon expanding and becoming less dense, because the volume went up, right? Just think of a water ball you put in a freezer, it expands. That ice stays at the top of the lake, the pond, or even the ocean and creates an insulative layer. Think about it. What's an igloo made out of? It's made out of ice. So you're telling me I want to stay warm, so I make something out of ice? Yeah, because that ice acts as an insulation layer. Okay? And then high specific heat. That's the heat that must be absorbed or lost to change the temperature of the water of the liquid by 1 degree. To change the 1 gram of water or whatever substance by 1 degree Celsius. Okay? We can wake up in the morning and it can be 30 degrees outside. By the afternoon, we can hit 70. That's a 40-degree change in temperature. You will not have a 40-degree change in temperature in the water right at that beach. That's not going to happen, right? Because it takes so much more energy to change the temperature of the water because it has a high specific heat. Desert, as much as 40-degree change in temperature is huge here in Florida, right, with our humidity, the desert can literally change 100 degrees from morning to night. It can be 30 degrees at nighttime, and during the day it can hit 130 degrees Fahrenheit. That's a 100-degree temperature change. Why is that possible? It's the desert. There's no humidity. There's no water in the air. So because of that, the air temperature can change much more greatly, right? We actually have a little bit better temperament, if you will, in our weather because of a high specific heat, I'm sorry guys, in the actual water, so that helps us out. And that is the end of chapter 2. Make sure you take your quiz.